My name is Chelsea Finn. I'm a new faculty at Stanford, and I work in artificial intelligence and robotics. And so I'd like to start by talking about some of what I view as some of the most impressive feats in artificial intelligence. This includes things like TD Gammon, like IBM Watson, helicopter acrobatics, AlphaGo, for example. And I think that the reason why these are so impressive to us is that all of these systems can perform a complex task very well, and sometimes even better than a human can perform that task. For example, if you had a friend that could translate seamlessly between two languages, or a friend that was the champion of Go, you'd probably be pretty impressed with that friend. They'd probably be pretty smart, and they could probably do a lot of other things too. But the same isn't true for an artificial intelligence system. So if a machine can translate between two systems, between two languages, that same machine can't necessarily comprehend a story or read a news article, for example. And so what I think is equally important to building these systems that can perform very complex tasks is systems that can be able to perform many different tasks, is generality. And in this light, I would view all of these systems on the top as what I would call specialists, things that are specialized for one particular narrow task, rather than systems that can develop a broader understanding of what's going on and being able to use that understanding to accomplish many different things. And so what I'd like to talk about in this talk is how we can build generalists. And it's worth mentioning that I think that generalists and systems that can do many different tasks on the surface are not necessarily going to look as impressive as the things that can do the very complex things. First, because if they can do many different things, we need to start off with simpler tasks and not these super complex tasks. And second, the systems are going to look the same. A system that can do one thing, you can't tell that the system that translates between two languages can't do other things because you only see it doing that one thing at one time. So in particular, what about simple things like simple manipulation skills? Enabling machines to be able to manipulate blocks in different ways and play with toys. It turns out that these simple yet general manipulation skills are beyond the scope of current machine learning and artificial intelligence methods. Even things like picking up Go pieces and placing them on a board are far beyond what our current systems can do today. And so it turns out that there's actually something called Moravec's paradox that says that the simpler yet broader capabilities are actually more challenging to accomplish in robots and in machines than the more complex things, simply because they're so intuitive to us and so ingrained from such an early age that we don't understand how to actually endow machines with the same capabilities. And so in this talk, what I want to talk about is, can we enable robots and machines to do a breadth of very simple skills? The things that are unimpressive on the surface, but hopefully in the future will enable us to build more general capabilities in AI systems in the future. Okay, so how can we build a robot that can do many different things? So I think to do this, we need to move away from learning policies in closed, narrow universes towards systems that are learning in much broader and more diverse settings. Learning general purpose models and using those models to plan to accomplish a wide variety of tasks. So the notion of building a predictive model and using that to plan to accomplish many different tasks isn't a new idea. So in model-based control, for example, in robotics, there has been for a very long time this idea that you can build some model of the world and then use that model of the world to reach different goals, for example. Now, what's new and what's going to be challenging here is being able to try to do this from raw pixel observations with limited supervision, and of course, being able to do all of that in the real world. And so what I'm going to talk about today in this talk is, first, can we learn structured representations that enable planning for a wide variety of long horizon tasks? And second, can we learn models of diverse open world environments to enable robots to accomplish a diverse range of tasks with a diverse range of objects? Okay, so let's first talk about structured latent space models. So this is work done in collaboration with the student Michael Janner and Jiajun Wu, among some others. And first I'll give an overview of how it works before going into some of the details. So the way this works is, first we collect a diverse range of interactions. These interactions, with more diversity, we can acquire a more general purpose model just because it's trained on a wider distribution of data. Second, we learn a structured representation from that data and learn a predictive model of what the future will be like based off of the current representation. And with increased structure, we can accomplish longer horizon reasoning because you don't have to predict kind of the unstructured observations into the future. And then lastly, once we have this predictive model of what will happen based on the actions that we take, we'll use it to plan. And by planning and be able to plan to accomplish different goals online, we can have the robot or a machine learning system accomplish these different tasks by planning for those tasks online. Okay, so what do I mean by some diverse interactions? Here's some examples in this work of the diverse interactions that we collected. This is in simulation, of course, but I'll also show results in the real world in a minute. And then once we collect this diverse data, we learn a structured representation. And in this case, what I mean by structured representation is that we're going to be learning an object-centric representation of the world and predicting into the future this object-centric representation. And then once we have that object-centric representation, we're going to use it to plan. And so, for example, we might want our robot to be able to plan how to make a tower of blocks here. But the goal will also be to build really any tower of blocks. Given in the image on the left, can the robot construct that using its model and its understanding of the world? Okay. So a couple of the details now. So the first question is, how do you actually go about learning this structured representation, and in this case, an object-centric model? There's been a couple of prior works that have looked at this problem. So, for example, Islami et al. Looked at learning object-centric models from unsupervised data of simple 2D scenes, while Wu et al. Looked at learning object-centric representations by using full supervision of all the object properties. And in this work, we're going to make one assumption regarding the supervision, which is that we're going to assume that we have the segmentation masks for the objects in individual frames. This is less supervision than was seen in prior work in Wu et al., for example, but we're going to be looking at much more complex 3D scenes than what was seen in prior work in Islami et al. Okay, so this is what the model looks like. So first, we take our image, we segment that image into the different objects in the scene. We then have a learned neural network that produces latent representations of each of the segmented objects. We then have a learned neural network again that's predicting forward what the object state or the object representation will be at future time steps. And then we have a third module that's used just for training to render those back out into images and compose it into a final frame. And then we train this model through a mixture of reconstruction loss as using both an L2 loss and a loss based off of visual features. Okay. So once we have this representation of objects and this model of how objects will work in the future, we can then plan using that model. And so in order to plan, we use a goal representation that's just an image of the object configuration. So say our goal is to make this tower of blocks. Then our action space is going to be where an object, which object to drop and where to drop it. For example, we might pick the purple block and to drop it right here. And then in order to plan, we use the predictive model along with a sampling-based beam search in order to plan an action sequence that will reach the goal. And then evaluate the action sequence based off of the distance in latent space as well as the distance in pixel space. And then after we take each action, we replan after each step. So what this looks like is we select this action, for example, we predict into the future what the resulting image or what the resulting object representation will look like. We then compare that to our goal and decide whether or not we want to take this action or not. In this case, this was the chosen action. And then we repeat at every single time step. So in this case, the model chooses to predict to place this purple block next, and so on and so forth, until the model figures out how to construct this tower based off of using its representation of objects and using its planner. Okay, so we took this method, and so yeah, again, each of these are showing the sampled actions and the one-step predictions. We took this model and we also applied it on a real robot. In this case, the goal images are all shown here. So the goals are to construct different towers of blocks in the real world. And here is the executions by the robot as it's planning to, in real time, as it's planning to place different blocks to try to construct these towers. And so what we can see is that in most of these cases, the robot figures out how to successfully place blocks in the correct order, knowing that it shouldn't pick the blocks on the top first, it should pick blocks that are located at the bottom first, and place them accordingly in order to create the different towers. And again, all of this is from kind of raw pixel observations, along with the segmentation masks that it receives. Okay, so the takeaways for me from this work is, first, that by learning a model of diverse interactions, we can accomplish not one goal, but many different types of goals, in this case, many different types of block towers. And second, by using a structured latent space, we can achieve more complex, longer horizon skills that wouldn't be able to be achieved if you use some black box model of the observation space. Okay, so now that we covered looking at structured representations for learning models, let's look at how we can try to tackle much more diverse environments where we have where you have hundreds of objects and much more diverse observations. Okay, so there has been some work on trying to learn in diverse environments through self-supervised learning. So for example, there's been a lot of work on learning to grasp with robots and learning to grasp many different types of objects, as well as learning to manipulate rope, for example. And our goal with this work will be similar to these prior works in that we want to also be able to generalize to novel objects. But what's going to be different is that we also want to be able to generalize to many different tasks. What's kind of different about this prior work is that the prior work was learning a policy for grasping. And if you wanted the robot to do something else, like manipulating ropes, that was basically an entirely different paper. And so instead, we're going to try to learn a general purpose model such that we can plan to achieve a wide variety of tasks. And the way that we're going to do this is, again, it's pretty similar to the last setup where we're going to collect data, learn a predictive model using that data, and then use that predictive model to plan to achieve many different tasks. Okay. So how can we collect diverse data? In this case, we want to be able to collect data in the real world that's quite diverse. And so in order to do this, we need to be able to let the robot kind of collect data autonomously. Because if the robot can collect data autonomously on its own, then it can experience much more diverse things, and we don't need to kind of be supervising it every step of the way. It can gather a much broader and larger data set. And so here's some examples of the data that we've collected on the robot. This is mostly just random actions and random grasping motions, for example, that are applied to the robot, and then the robot observes the images that are from its camera, as well as the actions that it's taking. And so one thing worth mentioning here is, in contrast to learning a policy or learning how to take actions, there's no notion of progress or success in this data. All you see is just kind of interactions with the world. And so if you wanted to use this autonomously collected data for learning a policy, it would be quite challenging. You don't have any reward that's being given to you or any feedback on how well you're doing. And that's true in general for a lot of undirected experience that humans have, for example, as well. So how can we try to go about learning from this data? Well, what we do is we learn how to predict the future, as I alluded to before. So we learn a predictive model of videos, as kind of shown here. The the horizontal axis shows different actions that the robot takes, and each video shows what the model thinks will be the future, what the future will look like based on the actions sampled by the robot. And so in contrast to things like learning to play Go or learning to play Atari, these models capture much more general purpose knowledge of the world because they're learning to kind of predict what will happen and learning about objects. And they use all of the available supervision signal, basically all of the supervision that's available within the pixels. Whereas if you're using a model-free method that's trying to learn a policy with deep reinforcement learning, for example, the only supervision signal you have there that you can learn from is the reward feedback, rather than trying to learn from all of the pixels themselves as supervision. And the other nice thing about trying to predict in pixel space, in contrast to the previous work, is that there aren't any assumptions about the representations that you need for a given task. And that means that we can apply the same type of model to deformable objects, for example. And this model can also predict what will happen if the robot grasps a towel, for example, and moves it to a new position. Okay, cool. So once we have this video prediction model, what we do is we use it to plan. And so the way that planning works in this case is, say this is our initial image. We consider potential action sequences from this image, maybe these two action sequences. Then we predict the future for each action sequence. So we might get these two futures, for example. And then we can pick the future that we like the best, that we want the robot to be able to achieve, and execute the corresponding future. And then we can repeat steps 1 through 3 to replan in real time. This is somewhat of a simplified version of the actual optimization that we perform, but it generally gets across the point of how we can optimize for actions that achieve a particular goal. Okay, and we refer to this as visual model predictive control in the sense that it's really just running MPC in the pixel space or in the observation space of the robot. Okay, so now you might ask, well, if we're going to be planning and kind of looking at a given future, how do we decide if a future is the best one or the future that we want to accomplish? This is particularly challenging in visual domains where you actually have to determine whether an image is something that you want to accomplish or not. So we've experimented with a few different ways for specifying goals to the robot. One example is selecting where we want the robot to move pixels. This is actually quite convenient to specify. For example, you can specify that you want the robot to move the apple onto the plate or to cover the object using the towel. We've also looked at providing an image of the goal, for example, showing the robot that we want it to grasp an object in a certain position. And then another example that we've experimented with is providing a few examples of success, for example, showing how we might tell the robot to put the fork to the right of the plate. Okay, given these goal representations, the way the full system works is first we specify the goal. In this case, we are specifying the goal by telling it that we want it to, in this case, fold the short, so move the red point upward in the image. We then run our planning procedure, visual MPC, with respect to that goal. And here's an example video prediction of what the model thinks will happen based off of the action sequence that it chooses. And then finally, here is what the robot actually executes on the robot, trying to figure out how to fold that part of the piece of shorts. Okay, so here's another example. So in this case, the goal is to cover the object with the towel, and the robot figures out that it should use its model to, it should basically grasp the left-hand side of the towel and move it to the right. And again, these are all with the same exact model. We're not kind of training separate policies for each one of these. In this case, we gave it a few examples of success, trying to show that we wanted to move the pencil case to be behind the notebook. We infer a goal classifier that's going to be operating on the images and determining whether or not it has succeeded or not. We then run planning with respect to that classifier to get a prediction that looks like this. And then we run planning with respect to, we run the action sequence that was chosen by the planner. So in this case, it figures out how to move its arm such that the object will move to the correct position. Okay, and one thing that I'd really like to emphasize here is that all of these tasks can be accomplished with a single model. So beyond all the tasks that I shown previously, we can use the same model for example, lifting objects, for manipulating shirts in different ways, for placing apples onto plates, for folding shorts, as I showed previously, for maneuvering objects into different positions, and for manipulating different types of towels, for example. This is really getting at kind of the generality of these methods. Although all of these tasks are super simple in comparison to playing Go or playing Atari, for example, the method is general in that it could be used to accomplish a wide variety of manipulation skills. Okay. And one other thing worth mentioning is that as we kind of push towards better generality and better and more diverse data, it means that we can bring these robots closer to real-world unstructured environments. And so what we did is we actually brought the robot in 2017 down to the NeurIPS conference and demonstrated these techniques to the researchers at the conference. And this included all of the planning with visual models that I just showed, as well as some of our research on one-shot imitation learning. And beyond the demonstration that we did at the conference, we also demonstrated this to high schoolers at an outreach camp through AI for All. And kind of tying things back to the beginning, the students in many ways were unimpressed with the demonstrations because the robots were only doing things that they were themselves capable of, although I think they all still had fun. Great. Some takeaways. First, I've been focusing a lot on how we can build agents that can do many different tasks, from pixel observations with very limited supervision, and doing so in the physical world. I showed how we can use structured latent spaces for learning complex long-horizon tasks, and how we can learn models of diverse open-world environments in order to generalize with significant object diversity and with minimal human supervision. So very naturally in future work, kind of a very natural direction to go in is to try to get the best of both worlds, where we can do both long horizon tasks as well as more diverse tasks. And we have some very preliminary work in this direction where we're trying to combine unsupervised interaction with diverse objects with diverse sets of demonstrations for different tasks, where we can use the demonstrations as supervision to be able to accomplish more longer horizon tasks. And kind of as a preview of this work, we were looking at tasks like this, where the goal is to move some objects to a different position, like to sweep them into a new position. We don't tell the robot that it needs to figure out first how to grasp the tool and then use the tool to sweep them to the corner. And by using the supervision both from the unlabeled interaction as well as the demonstrations, the robot can figure out that it needs to first grasp the tool before actually trying to push the objects to the left. And kind of focusing again on generality, our goal isn't just to learn this task, but to be able to use a variety of different tools in different ways. For example, using brooms, using hooks to push a lot of clutter, or using a sponge to wipe objects off of a plate, for example. And we can do all of this with the same model. And then lastly, in future work, we're interested in how we can build better, more useful models of the world. And so, for example, this includes things like incorporating uncertainty into these models, because as you move further and further into the future, there's going to be increased amounts of uncertainty about what will happen. And we've been looking at, for example, learning stochastic models of video prediction in order to model that uncertainty. Second is how we can adapt the model with a small amount of experience, such that when you see a new thing for the first time or a new object that behaves in an unexpected way, can you leverage a small amount of interaction to figure out the properties of that object, for example. And we have some initial work in this direction where we're looking to adapt models in very small amounts of experience online, for example, to when an agent has lost its leg or is going up a slope that it hasn't seen before. And then lastly, one natural direction to think about is how should we be modeling the reward? I showed a few different examples, such as trying to infer rewards from goal images, but I think that there's a lot more directions here in terms of learning better internal representations of goals and rewards. Okay, with that, I'd like to thank all of the students and my collaborators for this work. All the paper, data, and code is linked on my website. This is my Berkeley website, but it'll soon be changed to a Stanford website. And I'd be happy to take some questions. Thank you.
So in the examples you've shown in the execution stage, is it adaptive in that if the robot sees some deviation from what it predicted, does it adapt, or it just sort of goes all out according to its predicted state?
Yeah, so there's two ways to adapt. There's one way to adapt is to kind of recompute your plan and change your plan as you see new observations. And in basically all of the work that I showed, we do that. The second way to adapt is actually after you see a small amount of interaction with an object, actually adapt your model of that object, and then also replan. And we, in kind of our, in this work, that's exactly what we're looking at, is we're actually adapting the model online in addition to replanning and recomputing our sequence of actions.
Yeah, I just want to piggyback on that question. I didn't see any feedback loop going back in adaptability. Where do you have the feedback loop in your algorithm or whatever you're doing? There's a goal, right? If I'm folding a shot, right? Doesn't matter I fold which way. My goal is to fold that shot, right? So I can take any sequence. A robot can take any sequence, right? So I'm just looking for, is there any feedback loop in your learnability of robots, or where is the feedback is in that, the model which you presented? Because there is a goal, steps, and there's a plan, and robot is following that plan, right?
Yeah, so in real time, the robot is recomputing its plan at every step, yeah. And then there's the other form of feedback, which is actually after you've used your model to accomplish new things, you can then retrain your model on the new experiences that it's seen. And in some of the work that I showed in the future work slides, we've also been looking into doing that. Yeah.
Thanks. In looking at your decision to model in pixel space, it's definitely fascinating since it allows you to generalize to so much. I was also curious to see if you had also considered looking at any three-dimensional representations or models that also look at, can we segment an object similar to your first work and identify where it exists in 3D space?
Yeah, so I didn't mention this before, but actually in all of these examples, we're actually using 2 viewpoints. Which allow it to, and we do video prediction on both viewpoints, which allow it to do more 3D tasks. And this was actually pretty important to get it to grasp things, for example, because grasping things and then moving it away from the camera plane look identical if you just have a 2D image. So that's kind of one step towards moving 3D. We haven't looked at that's, I think, the most that we've done with 3D so far. I think that one of the challenges with 3D is, like, if you're representing objects in 3D, I think it's, like, I like the idea of using a latent representation better than trying to come up with some representation, because it's actually pretty challenging to think about how would you represent a shirt in 3D, or how would you represent an object in 3D, for example. Like, you could use voxel grids, you could use meshes, you could use point clouds, but none of those representations are really satisfying to me, and I think that by using learned representations, the model can figure out its own 3D representation.